Welcome back, folks. Today we're continuing our look at trigonometry, and today we're going to move beyond the basic review right triangle trig that you've seen before. We're going to get into finding trig ratios of any angle and hopefully blow your mind a little bit in the process. So here's what we mean when we say trig ratio of any angle. Okay, right triangle trigonometry, we have a right triangle. We'll say that one of the two angles in it is theta. And we talked about finding things like the sine or cosine or tangent of theta. We'll go with sine for now. And we define the sine of theta as equal to the ratio of the opposite side of the triangle to theta over the hypotenuse. Okay, so one way we can think about the sine ratio is as a function where I input an angle and I get out a unique ratio for that angle. And something we've always talked about with functions are the domain. In other words, what are my possible inputs? What values can I have for my theta? Now, if we're thinking in terms of right triangle trigonometry, smallest possible angle in a right triangle could be we could shrink that down to not 0, but anything above 0. Okay, once it gets to 0, the triangle disappears. We no longer have an opposite side. Okay, so we could say that theta has to be greater than 0. And then also as far as how small or how large this angle could be, okay, well again, if I shrink my triangle up the other way and that theta, that angle becomes 90, again my triangle disappears. So we'll say that our theta has to be less than 90 degrees. Okay, so far we've looked at trig ratios where that angle could be between 0 and 90. What we're going to get into today is forgetting about the 0 to 90, and let's say that we can look at angles up to infinity. Okay, that might not make sense as far as thinking about just a right triangle, but we'll show you how that makes sense in a little bit. And then we'll also talk about finding trig ratios for negative angles. So our goal here is going to be to expand the domain of our trig functions from negative infinity to infinity. Let's show you how to do that. Now the first step for expanding on our trigonometric definitions is going to be to take a different view of an angle. We're going to say it's a dynamic view of an angle. So we're going to think of an angle as something that's moving, something that's rotating, something that's opened up, rather than just the static set of rays. Okay, some vocab for that. We're going to say that the beginning position of our angle rotation is the initial side. Okay, the beginning ray. So here I have my initial side. Vertex is going to be kind of the center of rotation where my rays come together. And then the terminal side will be the final position. Okay, so we'll think of this angle as opening up from the initial side to the terminal side, okay, with a measure of angle theta. And then by that view, we'll say the measure of an angle is the number that describes the amount of rotation from the initial side to the terminal side. Okay, so our theta here is how much rotation, how much it opens up as I go from initial side to terminal side. Now the next thing we'll do with that new view of an angle is put our angles into standard position. And I have two different examples here of angles in standard position. We'll say standard position, an angle is in standard position when it is in the xy coordinate plane. So we have our x-axis, y-axis. Okay, the vertex is on the origin. So our vertex at 0, 0. Okay, and the initial side is on the positive x-axis. All right, so in both these cases here, my initial side, my rotation begins along the positive axis. Vertex is at the origin, initial side along positive x-axis. Okay, what this is going to allow us to do is to define both positive and negative angles. We'll say it's a positive angle if it has counterclockwise rotation. Or in other words, positive angle if it opens up to its terminal side. And then I'll say it's a negative angle if it has counterclockwise rotation. So in other words, it's a negative angle if it opens down from initial side to terminal side. This is going to lead to the idea of coterminal angles. Okay, angles with the same terminal side but different measures. And it's going to be coterminal angles that allow us to talk about angles that are greater than 360 or for negative angles less than negative 360. So as you can see here, I have an initial side along the origin and a terminal side in the second quadrant. Now there's going to be two different ways I can express this angle. One would be with a positive angle opening up. We'll call that alpha. Then as you can see, I also have a negative angle opening down, beta, which gets me essentially to the same spot. Okay, it's the same angle, two different ways to measure it with positive numbers and negative numbers. Okay, also what I could do is I could rotate a full rotation, so 360 degrees or 2 pi radians, and then keep going, okay, to that same position. Okay, we'll call that angle in this example theta. Okay, so theta is another way to draw the same angle, okay, with just a measure that's greater than the initial alpha, okay, greater than 360 degrees. Okay, so again, coterminal angles, the same angle, just with different numbers or different measures corresponding with them. That's going to be the first thing we look at solving for today, okay, finding coterminal angles. Problem 1 says find and draw two angles, one positive and one negative, coterminal with a given angle. Okay, so I'm given 200 degrees. Let's draw that in standard position to start off with. Okay, so for standard position, vertex is on the origin, initial sides along the positive x-axis, and it's going to open up because we're talking about a positive angle. Now the big question here is going to be which quadrant do we end up in? Now if we go up to the positive y-axis, that'd be 90 degrees, so we'll keep going. Okay, back down to the negative x-axis, that'd be 180 degrees. If I keep rotating then and stop before the negative y-axis, or 270, okay, that's going to be the correct quadrant. We know that 200 degrees will be somewhere between 180 and 270. Okay, so we'll say this is our 200 degree angle here. Okay, we want to find and draw two coterminal angles. Okay, we'll start by finding a negative one. All right, the negative angle is just going to be this angle right here. Okay, and to figure out its measure, what we'll do is we'll take 200 degrees and subtract 360 from it, which will leave us with a negative 160 degrees. Okay, so we get the same angle by going negative 160 rather than 200. Okay, again, same angle, two different ways to write it. All right, we also want to find another positive one. What I can do to get my next positive angle is take the original 200 degrees, and instead of subtracting 360, we'll add 360 to it. We'll add a rotation. Okay, so 200 plus 360, that's going to give me a 560 degrees. And essentially what that'll look like is spin around the coordinate system one full time, 360 degrees, and then keep going an additional 200, okay, to end up at that 560, as my picture becomes a mess here. Okay, now if this problem was looking for additional positive angles, what I do is just keep on adding rotations or adding 360. Or if I wanted more negative angles, I just keep subtracting 360, okay, from that first negative angle. All right, why don't you pause the video, give part B a shot, and then hit play to check the answer. All right, now the trick with part B is that negative 510 degrees is less than negative 360. So it's more than one wrap around the coordinate system. So what I'd recommend to do with this one is don't try to draw negative 510 right away. Let's find a kind of greater negative angle and draw that first. Okay, so I can find another negative angle by taking negative 510 and adding 360 to it. Okay, that's going to give me a negative 150. And like I said, it's going to be easier to draw that negative 150. So we'll go standard position. We'll go down 90, okay, stopping short of 180. Say here's a negative 150 degrees. And adding 360 didn't give me a positive angle, so what we'll do is we'll add 360 again. Okay, so negative 150 plus 360, which is going to give us a 210 degrees for a positive angle. All right, this smallest positive and greatest negative angles are going to be the two easiest ones to work with. Okay, I can still graph this negative 510. What that would be is the negative 150 degrees, okay, minus another rotation. That's what the negative 510 degrees would look like. For part C and D, we're going to do the exact same thing, except for this time we're working in terms of radians instead of degrees. Now what you could do for a problem like this is simply convert the radians to degrees, okay, add 360, subtract 360, and then just convert back for the answer at the end. All right, but what we want to do is be able to work in terms of radians, so let's show you how to do that here. So same idea, I'm going to draw my angle in standard position. Okay, starting along the positive x and rotating up because we have a positive radian measure. Now the thing to remember about radians is that 180 degrees is equal to pi radians. Okay, meaning that 90 degrees will be equal to pi over 2. Okay, so 270 then equals 3 pi over 2, and 360 degrees equals 2 pi rads. Okay, so we can kind of use that as our landmarks. 5 pi over 6, that's less than pi, but greater than half pi, greater than pi over 2. So I know that my angle is going to end up somewhere in that second quadrant here. We'll say that's what 5 pi over 6 looks like. And then the same way we can find positive, negative angles. For a negative one, I'll take the original 5 pi over 6 and simply subtract the rotation. But instead of minus 360, since we're talking radians, we'll subtract 2 pi. Okay, we can say 5 pi over 6 minus 12 pi over 6, if we want a common denominator, which would just be a negative 7 pi over 6. Okay, so this negative angle here would be 7 pi over 6, which makes sense because 6 pi over 6 would be a pi. All right, so 7 pi over 6 would be just a little bit past that. And don't forget the negative, we mean negative 7 pi over 6. We can find another positive angle in the same way. If I take the original 5 pi over 6 and then add a full rotation to it, add 2 pi. In other words, 5 pi over 6 plus the 12 pi over 6 again, that'll give me a 17 pi over 6. All right, so one full rotation plus the pi over 6 will give me that 17 pi over 6. All right, D is the same idea. I want you to take a second, pause the video, work your way through that, and then hit play to check your answer. Let's start by graphing the 7 pi over 3. Okay, and we'll use the same landmarks, the pi over 2, the pi, the 3 pi over 2, and 2 pi once again. Okay, as I start rotating around, when I get to pi, okay, that's the same as 3 pi over 3. Okay, so let's keep going. Continuing to 2 pi, all right, in terms of thirds, that would be a 6 pi over 3. Okay, so we'll keep going. So 2 pi is 6 pi over 3. We have 7 pi over 3. So we have here then is a pi over 3 more than the 2 pi. All right, so my 7 pi over 3 is going to look somewhere like this, wrapping all the way around, coming back to the first quadrant. Okay, we just kind of alluded to how we can find the next positive angle or another positive angle. If I take that 7 pi over 3 and subtract 2 pi from it, that's going to leave me with just a pi over 3, okay, which would be this positive angle right here, okay, kind of the smallest possible positive angle. We can next find the negative angle. We'll take that pi over 3 now, and again subtract 2 pi once again, subtract a rotation. So pi over 3 minus 6 pi over 3, that's going to give me a 5 pi over 3. All right, so our negative angle here will just be a negative 5 pi over 3. All right, with what we've done with coterminal angles, we're now ready to evaluate trig functions of any angle. Here's how we'll do that. We'll say let theta be an angle in standard position. Okay, so we have an angle in standard position, the second quadrant, and alpha be the corresponding acute angle formed by the terminal side of theta and the x-axis. Okay, we'll call that a reference angle. Okay, so we'll always make the alpha reference angle with the terminal side of our angle we're talking about and the x-axis. Okay, then the value of any trig function of theta is just equal to the value of the trig function of the alpha. Okay, so in other words, instead of evaluating our trig function for this theta greater than a right angle, we'll use the acute angle alpha, which will allow us to make a right triangle and apply our same trig definitions. Okay, now the reason we always use the x-axis is by using the x-axis when we're talking about acute angles, the theta will just be equal to the alpha, and our original trig definitions will apply. Let's take a look at how to do that. All right, so problem 2, part A says evaluate the trig ratio. We have the sine of 315 degrees. Okay, obviously 315 is greater than 90. Okay, so we're not just talking about a simple right triangle here. We'll start by graphing that 315. Okay, so we'll start on the positive x for initial side. We'll rotate 90, 180, 270, and 315 is going to be somewhere here short of 360, a full rotation. Okay, the next thing we'll do is we'll find this reference angle with the x-axis, and again, always with the x, never with the y-axis. Okay, and that angle alpha, the way we'll calculate in this case is we are short of 360. So we'll go 360 minus 315 degrees, which will give us a 45 degrees. All right, so our reference angle is 45. From this reference angle, we'll construct a reference right triangle. And now if one angle is 45, another is 90, I know that the third angle will be 45 as well. Okay, and this is our 45, 45, 90 right triangle, which I know the side lengths for. The legs are both 1, and the hypotenuse is root 2. Now, when placing a triangle on the coordinate system, we do need to pay attention to which direction we're going in. I'm going to say that this adjacent side to our reference angle has a positive length, okay, because it's moving in the positive x direction. I'm going to say the opposite side, though, has a negative length because it's moving in the negative y direction. And then we'll say the hypotenuse is positive because it's not necessarily going in a y or an x direction. It's more of a distance between 2 points. Okay, distances are always positive, so the hypotenuse is always going to be positive. Okay, from there, once we have this reference triangle set up, we're just going to evaluate the sine of this reference angle 45 here. Okay, sine is opposite over hypotenuse, so opposite is a negative 1 over hypotenuse root 2. So we get a negative 1 over root 2, which we can rationalize. I'll multiply by root 2 over root 2 to do that, which gives us just a negative root 2 over 2. All right, so that's how we use our coterminal angles and a new definition to evaluate trig ratios that go beyond 90 degrees. Let's take a look at another example. Part B, we want to evaluate the cosine of negative 210 degrees. So this time we're looking at trig ratios of negative angles. Once again, we'll start by graphing that angle out. Initial side on the positive x-axis. Negative angles will rotate down, 90, 180, and 210 somewhere in the second quadrant, short of negative 270 degrees. Then once again, what we want to do is figure out what that reference angle is with the terminal side and the x-axis. Okay, we'll call that our alpha once again. And here to calculate alpha, what we'll do is we'll think in terms of positive angles. We're 210 degrees and we're past 180. So we want to figure out what the difference of 210 and 180 is. So I'll go 210 minus 180, which gives me 30 degrees. Okay, so in this case, my reference angle is a 30. Once again, from that reference angle, we'll make a reference triangle. If I have a 30, 90, the other angle will be 60. Okay, so this is our 30, 60, 90 reference right triangle. I know its opposite side is a 1. Opposite to the 30 is 1. Opposite to the 60 is a root 3. I'm going to make that negative because we're in the negative x direction. Okay, the 1's positive because that's moving in the positive y direction. And hypotenuse of that 30, 60, 90 right triangle is just the 2. Okay, so evaluating this then, again, we'll look at the cosine of this reference angle, this 30. Cosine is adjacent over hypotenuse. So adjacent is a negative root 3 over hypotenuse 2. So we'll say the cosine of negative 210 degrees is this negative root 3 over 2. We're going to look at a few more examples. Part C, we want to know the tan of 4 pi over 3. So here we're looking at evaluating trig ratios for angles measured in radians rather than degrees. Okay, first thing we might want to do is convert this radian measure to degree, just to help us kind of graph it and be more comfortable with it. Remember, the way to do that is I'll take my 4 pi over 3 and I'll multiply it by 180 degrees over pi. Okay, pi's will cancel, so we'll go 4 times 180 divided by 3. That's going to give us a 240 degrees. So in other words, here we're looking at the tangent of just 240 degrees. Once again, we'll graph that angle in standard position. Okay, 240 is going to rotate past 90, past 180, and fall short of 270. Somewhere in that third quadrant. Again, we want to figure out this reference angle. And for that, what I'll do is we'll say the alpha is equal to 240 minus 180 once again. In other words, 60 degrees. So this time that reference angle is 60. I'll use that reference angle to create my reference triangle with a 90, 60, and 30 degree angle. Okay, so same one we had last time. Across from the 60 is going to be the square root 3, and they'll be negative. Across from the 30 is going to be the 1, and they'll be negative as well, because that's negative x direction. And then hypotenuse will be the root 2. All right, so finding the tangent of this 60 here on our reference triangle. Tangent we know is opposite over adjacent. So that's going to be a negative root 3 over negative 1, which in other words just reduces down to positive root 3. Okay, so in this case we saw that even though we're doing something that's not an acute angle, we still do get a positive answer. Okay, last question, we'll do the same thing just with a little bit messier of an angle. Okay, 23 pi over 6. First thing you're going to want to do is convert that to degrees. Okay, so 23 pi over 6 times 180 degrees over pi. Okay, pi's cancel. 23 times 180 divided by 6. That's going to give us a 690 degrees. All right, now 690, since that's more than one rotation, I'm going to subtract 360 from it to try to get it down to less than one full rotation, which will give me a 330 degrees. Okay, so when we say find the secant of 23 pi over 6, that's going to be the same thing as the secant of 330. Let's go through that process one more time. We'll graph that angle in standard position. .330 opening up, that's going to land us in the third quadrant. Short of a full rotation, short of the 360. Reference angle in this case, we are 30 degrees short of that 360. So once again, we have our 30, 60, 90 right triangle. Labeling the sides, across from the 30 we have a negative 1. Across from the 60 will be a positive root 3. Okay, 1's negative for the negative y direction. The root 3 is positive for the positive x. And then hypotenuse is a 2. All right, and secant is hypotenuse over adjacent. So hypotenuse will be a 2. Adjacent side to that 30 will be the root 3. And we can rationalize that by multiplying by root 3 over 3 to leave us with a 2 root 3 over 3 for final answer.